When tapping a mobile app button, the screen updates in a fraction of a second. Underneath, a massive, highly coordinated system works at light speed. For many computer science students, web development can feel like a disjointed exercise in memorizing tools like React, Node, MongoDB, and AWS without seeing the connective tissue. Functional web applications operate as single, continuous pipelines of state management, asynchronous routing, and elastic infrastructure. To see how this works, we'll build a master architectural grid divided into 4 zones: client, cloud infrastructure, server, and database. We will trace a single HTTP request across this grid, mapping every step directly to the architectural patterns from your exams. Mastering the communication across this pipeline is the ultimate key to both passing high-yield exam questions and architecting scalable software in the real world. We start on the left side of our grid, the client. In modern development, we followed the mobile-first paradigm, engineering the UI for constrained screen sizes and touch events before scaling up to a desktop environment. To manage the complexity of these interfaces, we use the Model View Controller, or MVC, architecture. This pattern strictly separates the underlying data logic from the visual presentation you actually see. While legacy tools like jQuery focused on direct manipulation of the document object model, modern frameworks like React and Angular are built on reusable, self-contained components that can scale to enterprise levels. React uses hooks, specifically useState and useEffect, to bind data to the UI. When a user interacts, data state changes, and React refreshes only that specific component piece, while the rest remains static. This interaction triggers a REST HTTP API call, packaging the state and firing it across the internet towards the backend. The modern client's primary job is maintaining a seamless UI state and securely firing requests off device without freezing the user screen. Our HTTP request has left the device and is now traveling across the public web toward our server, which means we are entering the cloud infrastructure column. To protect the server from the open internet, the request must first pass through an AWS Virtual Private Cloud, or VPC. This secure network isolates our backend into public and private subnets. At the ingress point sits the Elastic Load Balancer, catching the incoming wave of HTTP requests. It dynamically distributes traffic across backend targets, preventing server overload during high traffic periods. Those targets are Amazon EC2 instances, located in the private subnet. The EC2 instance is the raw compute engine, where the application code actually lives. Engineers connect to and configure these remote servers using secure shell protocols, often relying on tools like PuTTY to access the command line. A modern AWS deployment creates an elastic infrastructure that guarantees high availability even when user traffic spikes unpredictably. Let's zoom into one of those EC2 instances. This is our third column, the server. Here, we are running the Node.js runtime environment. As the request arrives, it is caught by ExpressJS. This middleware layer reads the request and routes it based on REST HTTP methods like get, post, put, or delete. This creates an architectural tension known as the single-thread paradox. Node.js operates on a single thread, yet it must handle thousands of simultaneous requests without blocking. The Node event loop has a call stack, web APIs, and a callback queue. Heavy database tasks are delegated to web APIs, instantly freeing the stack. Completed tasks enter the callback queue. The event loop pushes them back to the stack to finalize the response. Node.js achieves concurrency by never blocking its single thread, making it ideal for the high-volume routing required by REST APIs. To retrieve data, the backend query exits the server and hits our final layer, the MongoDB database cluster. MongoDB is a NoSQL database. It replaces the rigid tables of traditional SQL with a flexible, document-based structure. MongoDB stores data as JSON, mirroring the React front-end state structure for efficient transfer. It performs 4 CRUD operations triggered by the Express server's REST methods: post creates data, get reads, put updates, and delete removes. Using NoSQL and JSON creates a frictionless data language that flows from the database all the way to the user's mobile screen. Look at the master architectural grid. All 4 columns are now fully populated. A single packet starts iClient hook, routes through the ELB, is processed by the non-blocking event loop, updates the JSON database, and returns to the UI. As we have seen, every layer has a distinct role. The front end manages state, the cloud ensures scalable ingress, the backend routes asynchronously, and the database persists data flexibly. To apply this to your exams, analyze each question to determine if it is testing state, scale, or concurrency. Once you locate the problem on this grid, the answer becomes clear. Ultimately, true full-stack engineering focuses on the boundaries and communication protocols that hold the entire modern web together.